today I'm going to go through the sort of state of our research into the measurement of amine breakdown products from post-combustion carbon capture plant. Just a quick run through of what we're going to do. NPL's been researching into various areas of CCUS. We'll actually also have a look at a PCC plant and how it operates, because that feeds into the story of where the challenges come from. And then looking at the expected emissions and the flue gas characteristics and how all these make PCC plant actually very difficult plant to monitor, specifically for amine breakdown products, nitrosamines and nitramines. And so we'll look at the work we've done today and then the direction for future research, or where we think that direction should go. So as I said, NPL has been, I work for what's called the Environmental Emissions Metrology Group, and we have activities focused on various parts of the whole CCUS process. So looking through not just point source emissions, but also fugitive emissions. So things like leak detection and fugitives from CO2 infrastructure, and this is from right down from component level right up to site-wide fugitive measurements. And for that also simulating CO2 leaks and creating reference leaks to be able to validate these measurements. We've also been looking at the measurements of low levels of CO2 in exhaust stacks, because most emissions monitoring equipment is certified with much higher concentrations. And finally, looking at the measurements of amine breakdown products, and that's really what we're going to look at today. It's also what I think is possibly one of the most challenging things to measure. So for those of you who aren't familiar with it, when we're talking about post-combustion carbon capture, this process which involves an absorber and a stripper and uses an amine-based solvent, usually monoethyl amine, although there are quite a few proprietary, fairly secret solvents out there used to absorb the carbon dioxide. So I'll give a quick run through. So your combustion gas coming from your process enters the absorber at the bottom, flows up to the exhaust at the top. Meanwhile, you have a counterflow of the amine-based solvent going down and absorbing CO2 from the gas as it passes up. And this reaches the bottom and becomes what's called the rich solvent with the CO2 absorbed, and that passes via a heat exchanger into the stripper unit, where the CO2 is stripped out again to create fresh lean solvent, which is then passed back into the absorber. And obviously we get CO2 product out of the stripper side, which is purified, dewatered, and either sent for storage or use. So when we talk about pollutant emissions, we can sort of divide things into primary pollutants and secondary pollutants. So the primary pollutants are usual suite of pollutants, and obviously dependent on what combustion process is feeding the carbon capture process. And so we're looking at things like NOx, CO, HCl, HF, VOCs, potentially SO2, but also what might be absent are things like particulates, because it's been known that very fine particulate, ultrafine particulate rapidly degrades the solvent in the process. And for the same reason, sulfur trioxide, again, can form a very fine fume, which rapidly degrades the absorber solvent. And this is why potentially SO2 could well be scrubbed out before the exhaust gas hits the carbon capture process. Obviously, we're looking at CO2 as well, but at much lower levels than normally seen in combustion processes. And then when we look at the secondary pollutants, these are formed by an interaction between the absorber and the pollutant gases coming from the combustion process. And so these typically quite a lot of ammonia and various species of amines. Nitrosamines, which are nitrosated amine, which are produced by interaction with NOx and stat gas. There are a whole suite, varying toxicities, and then there are a whole bunch of primary, secondary, and tertiary amines as well. So we look at the flue gas characteristics, generally cooler, 35 to 45 degrees C, saturated gas with entrained droplets, and these droplets are potentially reactive because they will potentially contain the absorbing solution, and therefore they are quite challenging to monitor. Looking at the characteristics of the pollutants themselves, one of the big things is that it's been known that the absorber solution will degrade above 120 degrees C, and this actually has an impact when carrying out emissions monitoring because it affects how much you can heat a sampling train. There are also potentially, obviously, ongoing reactions with other components in the exhaust gas, so you potentially have reactions going on within your sampling train. Again, something that's not generally considered ideal for stack testing. And also secondary pollutant composition can change over time depending on the age of the solvent being used. So from one measurement campaign to the other, things might change. And also there are a wide range of physical characteristics in these compounds, as we shall see. So impact on sampling from these characteristics: saturated gas generally takes multi-point isokinetic sampling for manual sampling. The thermal reactivity, so this limits your sample train temperature, which means you potentially might have droplet within the heated elements of the sample train. And this also limits the effectiveness of using dynamic dilution for things like 13649 testing onto for solid adsorption. So our research started a few years ago. Initially, we looked specifically at nitrosamines, and we looked at validating the two most commonly used methods from a sort of literature survey for measurement of nitrosamines in various experimental and research programs. So these were the